Hi, Brian Miller-Hicks here, continuing series of Earth Science and Geology, and with a concentration today on the atmosphere, which is one of the four spheres of this planet: the atmosphere, the geosphere, the biosphere, and the hydrosphere. The atmosphere obviously actually contains elements of the hydrosphere in the form of water vapor, moisture. Okay, so what is the atmosphere? Well, obviously, we need the atmosphere. It is essential to our survival because it contains the gases which we breathe every day, hour by hour. We'll talk about what the atmosphere is made of, but consider that it's that thin shell of gases that surrounds our planet and allows us to survive. The gases in the atmosphere exchange with gases in the ocean. There's a very intimate relationship between the oceans and the atmosphere. And of course, the atmosphere is where our weather and our climate are generated. The atmosphere is layered. It actually has a structure, and the lowest layer in that structure actually contains our weather. We'll talk about that as well. So where did the atmosphere come from? Well, go back 4.6 billion years ago. The Earth was a ball of molten rock, gradually started cooling. As it cooled, the gases contained within the magma began to release when volcanoes started forming and outgassing some of these gases. The early atmosphere, some 4 billion years ago, was very toxic to beings like us. When it first started being released from the Earth, there was no life existing till a little bit later. Initially, our primitive atmosphere was methane, carbon dioxide, other gases, but there was very little free oxygen. That came later when organisms in the ocean began releasing free oxygen into ocean waters, which eventually made its way up into the atmosphere. So this is what our Earth's atmosphere is made of, primarily made of nitrogen. Almost 80% of our air is composed of nitrogen, not oxygen. Oxygen is about 21% of the gases in our atmosphere, in our air. Then we have a little bit of carbon dioxide, some argon, and other gases, which you'll see in this list here. Now, the proportions of gases in the atmosphere have not remained constant throughout geologic history. There were times in Earth's past when oxygen was a much higher percentage. Interestingly, oxygen levels were much higher during the times of dinosaurs, and that's one of the reasons why we had such gigantic creatures living at that time. Okay, so what does this depict? This depicts a geologic formation of rock, which is very, very rich in iron. It's very old rock dating back to the Precambrian. 2Ga means 2 billion years old. So why am I showing this when I'm talking about the atmosphere? Well, 2 billion years ago, the atmosphere was oxygen poor until organisms in the ocean started taking oxygen from being locked up in the elements of the earth and actually started extracting it and releasing it as a waste product into the ocean. So the ocean became oxygen rich. And at that time, the ocean was also rich in iron. That amount of abundant iron and abundant oxygen combined to form oxidized iron or rusty iron, which you see in this rock. So this rock contains and is very rich in abundant iron oxide from the oxygen combining with the iron at that time. Then when the ocean became so enriched in oxygen, it started releasing oxygen up into the atmosphere, which kick-started evolution in terms of oxygen-breathing organisms which now could live on land. So another component of our atmosphere that I haven't mentioned, actually water vapor is also a component, as well as aerosols. Aerosols are any tiny little particle in the atmosphere which contribute to smog, pollution, and dust and obscuring of the atmosphere. You can have many, many dust particles released from windstorms on the surface of the earth that can go into the atmosphere and become aerosols. Aerosols do a couple things. They can act as particles around which water droplets condense to form clouds and rainfall. And they can also carry dust across wide swaths of the Earth's surface and actually reflect sunlight or scatter sunlight. This effect of scattering and reflecting sunlight we see in our colorful sunrises and sunsets, which are primarily this colorful because of dust in the air. Let's look at the structure of the atmosphere. As I mentioned, the atmosphere is layered. It consists of a number of layers, which we'll get to in a minute. But first, I want to tell you that the atmosphere varies according to the pressure of the atmosphere, varies according with altitude. At the Earth's surface, the pressure of the atmosphere on us, on our bodies, is about 14.7 pounds per square inch. As you go higher and higher, air pressure decreases steadily, and then it decreases less steadily or less rapidly, but still decreases. The reason for this is air has weight. So at the Earth's surface, we have the combined weight of all the air above us pressing down on us at a pressure of 14.7 pounds per square inch. At an elevation of about 3.5 miles above the Earth's surface, air pressure is about 50% of what it is at the Earth's surface. Okay? The red line denotes pressure, steadily decreasing as you go upwards. So that if you're at the top of Everest, the air pressure is 314 millibars. That's another measure. It's another way we measure air pressure. Not in pounds per square inch, but in millibars of mercury. That goes back to our first barometers, which recorded air pressure. In these first barometers, there's simply a reservoir of mercury and a tube stuck in the middle of that reservoir. As the air pressure increased or decreased, the level of mercury would go up and down in that tube. So a couple other interesting things about air pressure as it decreases as we go higher and higher. You note that at 36 kilometers or 22 miles above the Earth's surface, air pressure is effectively almost zero because there's so little air up there. All right. In 1961, a U.S. Air Force captain, Captain Kittinger, took a balloon up to a height of about 20 miles, and then he jumped out, free fall, with a parachute, of course, which this record stood for quite a while until in 2012, some 52 years later, a person named Felix Baumgartner jumped out at an elevation of 24 miles. And then 4 years later, 2016, Mr. Alan Eustace jumped from an altitude of 26 miles. So the current world record of jumping, free falling from a height belongs to Mr. Eustace. In 2016, he jumped from 24 miles. I'm sorry, 26 miles. It's a pretty gutsy thing to do. And that record still stands. So here's how the structure of our atmosphere looks. It's got 4 basic layers. The lowest layer is called the troposphere. And that layer, from about 0 to 7 miles above the Earth's surface, is where most, if not all, our weather occurs. That's where rainfall occurs, thunderstorms, lightning, hurricanes, typhoons, tornadoes. Then we go to the next higher layer, which is the stratosphere. It's a very quiet zone where very little weather occurs. Up above that is the mesosphere, and then the thermosphere. Let me talk about some of the variations and changes you see from layer to layer. The red line is temperature variations. So at the Earth's surface, let's say it's about 70 degrees Fahrenheit. At the top of the troposphere, the temperature has steadily decreased to now a temperature of minus 70 degrees. The reason why temperature decreases steadily as you move away from the Earth's surface is that the Earth's surface absorbs heat from the sun, but as you get farther and farther away, that heat has escaped from the Earth's surface to where it's very, very cold at that altitude, at the top of the troposphere. The contacts between the various layers, the troposphere, stratosphere, mesosphere, are labeled as pauses. So that contact between the troposphere and the stratosphere above is called a tropopause. What's happening in the stratosphere? Well, you'll see actually temperatures increasing again. That's primarily because in the stratosphere we have a gas called ozone, which is O3. It's a form of oxygen with 3 oxygen atoms forming an oxygen molecule, whereas free oxygen that we typically breathe is O2 with only 2 atoms. So the presence of ozone actually helps the atmosphere retain heat to where at an elevation of about 30 miles, the temperatures at that elevation are almost as warm as the temperatures at the Earth's surface. Then what happens in the mesosphere? In the mesosphere, temperatures radically decrease again because we're very far away from Earth, and there's very, very little gas. There's very few atoms or molecules of air in the mesosphere, so the temperature again decreases. However, there is still enough gas in the atmosphere to where when meteors hit this layer, they burn up from friction with by interacting with whatever air molecules are up there. And finally, the top layer is the thermosphere. Thermo means heat, and the thermosphere actually has the highest temperatures in our atmosphere. Temperatures increase again. Why? Well, you're getting closer to the sun. Now you're at 90 miles above the Earth's surface. And there's so little air, there's so very few air molecules that the sun's heat is unimpeded, the sun's radiation. However, a weird effect of this is if you were able to be up here in the thermosphere without a spacesuit, which is not possible because you wouldn't be able to breathe, but if that were possible, you would feel very little heat on your skin because there's so few air molecules to transmit that heat. So we have a kind of a weird back and forth of cooling, heating, cooling, and heating as we go up through the layers of the atmosphere, all the way from troposphere to thermosphere. This picture you see here is an aurora. An aurora is a phenomenon that's caused by the excitation of gas molecules in the thermosphere by the influence of solar particles interacting with these gases. And you'll see brilliant displays of color at primarily the north and south polar areas, as there's sort of a hole in the magnetosphere, the magnetic field that surrounds the Earth, so that solar energy can come in and interact with the gas molecules at the poles. Now, the atmosphere, of course, is composed of gases, we know that, composed of oxygen, nitrogen, water vapor, carbon dioxide, and others. Turns out that the weather on our planet, the interactions of atmosphere, the variations in temperature in the Earth's atmosphere are very much influenced by our relationship with the sun. The sun, of course, is our little furnace, not little, actually it's quite large, 93 million miles away, which gives us our light, which gives us our heat. Without the sun, of course, we would not be able to survive as well. We'd be trapped on a cold, very dark world. But the relationships between Earth and Sun have a lot to do with how our weather and our climate behave. What we know about our Earth is that it spins on its axis. We have a north-south axis, but this north-south axis is not upright, is not vertical in relationship to its orbital plane. By orbital plane, I mean that plane that the Earth orbits around the sun. If you imagine the orbital plane going through the center of the Earth like this, left to right, being flat or horizontal the way I'm indicating it, the Earth's spin axis is actually inclined from the vertical now of about 23.5 degrees. That varies somewhat through time. But what that has an effect on is the heating of our planet's surface. It results in unequal solar heating of the Earth. What we're looking at here is the Earth during a southern hemisphere summer, because it's pointing, the southern hemisphere is pointing towards the sun, and a northern hemisphere winter, because the northern pole of the axis is pointing away from the sun. So at the very top, at the North Pole, the sun's rays have to travel quite a distance to get through the Earth's surface. That sort of robs the sun's rays of energy, whereas at the equator, over here, the sun's rays travel through a shorter distance. There's a more direct impact, a more increased solar radiation, and therefore an increased solar heating from the sun as compared to the very slight solar heating here. You see the sun's rays going through a lot of the atmosphere and then hitting the Earth, but at a very shallow angle. Whereas here, the sun's rays go through less of an atmosphere and hit the Earth more directly. The maximum amount of solar energy hitting the Earth at this time, as depicted in this graphic, is at 23.5 degrees latitude below the equator. This is the most direct sunlight. Okay, so there's that. The Earth's energy, heat, and weather are also influenced by the Earth's journey around the sun as it orbits around the sun. If we look at the sun in the center, and we know the Earth orbits around the sun, right? In the northern wintertime, December 21st to 22nd, that's known as the winter solstice. The sun is vertical at that latitude of 23.5 degrees south that I just showed you. Maximum solar energy on December 21st is directed at that area of the Earth. But us in the northern hemisphere, and if we're looking at Southern California, it's somewhere in here, the solar radiation is less and temperatures are colder during that time. If we swing all the way around to the summer solstice, that's when the northern axis is tilted or leaning towards the sun, so we get more solar radiation at that time. Okay. One thing I need to mention is that daytime during the winter solstice of the northern hemisphere, the days are shorter and the days are longer in the south. That's reversed in the summer solstice, where days are longer in the northern hemisphere and shorter in the southern hemisphere. If we look at the equinoxes, the spring equinox, March 21st and March 22nd, and the fall equinox, September 22 and 23. Equinox means equal night. So that means day and night in both the northern and the southern hemisphere are equal. We get 12 hours of daylight and 12 hours of nighttime as the Earth spins around its axis at the spring and fall equinox. Illustrate that a little bit further with daytime hours, number of hours. So let's look at the northern hemisphere summer, the June or summer solstice. So the Earth's axis is pointing towards the sun. That means at the North Pole, you're getting 24 hours of daylight. The Earth is spinning around its axis, but it's never going into shadow at the North Pole. The sun is illuminating the North Pole constantly, 24 hours a day. The opposite case, because the South Pole is leaning away from the sun, the South Pole is getting 24 hours of nighttime. And then we get everything in between, 24 hours of daylight, 24 hours of nighttime. At the equator, we get an even 12 hours of daylight and 12 hours of nighttime. The illuminator, that line between night and day, is evenly divided between daylight and nighttime, half and half. In the northern hemisphere, let's say at 40 degrees, no, let's pick 23.5 degrees latitude, which is about what Southern California is, more or less. We get a full 13.5 hours of daylight, which means we get 10.5 hours of nighttime. Okay, and the effects are reversed during the wintertime and during the spring and autumn equinox again, because the poles are neither tilting towards or away from the sun. They're vertical in relationship to the sun here. We get an even 12 hours of daylight, 12 hours of nighttime. Okay, let's get into radiation from the sun in a little more detail. Radiation, there are many types of radiation, all the way from shortwave radiation to long-wave radiation. Light itself is a form of radiation. Okay, so radiation is heat energy and light energy combined. We look at something called the electromagnetic spectrum. It varies all the way from very, very short wave gamma rays to long wave radio waves. Now, if you're looking from left to right, you're going from high energy to low energy. Gamma rays have very high energy, very high frequency. That means the wavelengths are short, frequency is high, energy is high. Radio waves, wavelength is long, energy is much lower. Somewhere within this scale from gamma rays to long radio waves, we have visible light. The only light, the only radiation that we can see is between this arrow and this arrow. It's not a very broad part of the electromagnetic spectrum, but it contains all the light that we can see, all the way from violet to red. So violet or bluish light has a higher energy, shorter wavelength, higher frequency than red light. Red light has longer wavelength, longer frequency, and less energy. So you go from high energy, short wavelength blue to long wavelength red. And we have other types of radiation that you're all familiar with. X-rays are pretty high energy. Ultraviolet and infrared are primarily heat waves, microwaves, so forth. Now, you don't want to be exposed to anything left of violet light. You don't want to get exposed to too much ultraviolet, too much X-rays, too much gamma rays. That radiation is such a high energy radiation that it can damage tissue. In the atmosphere, what happens to the radiation that comes from the sun? Well, some of it gets reflected off water vapor or aerosols in the atmosphere. Some of it gets scattered. We've already seen that in our photos of sunset and sunrise. In the atmosphere, we have scattering and reflection. So let's look at a clear sky. The sun's rays, radiation, come through the atmosphere. They're not impeded by anything much. Most of it reaches the ground, 80%. Some of it is absorbed by water vapor and dust. Some of it's scattered, but only 3%. On a cloudy day, we get a pretty different interaction. We get 30 to 60% of the light's reflected from a cloud, 5 to 20% is absorbed by clouds. Only 10 to 45% actually reaches the ground. So as you may imagine, and it makes sense, then on a cloudy day, less of the sun's radiation, less of the sun's light and heat actually reach the ground. So of the light and heat that reach the ground, we know that certain surfaces reflect or bounce more of that energy back because of their color and their lightness in terms of color. So clouds, because they're water vapor, which is reflected, and their fact that they're white, they reflect a lot of radiation, 70 to 80%. The ability of a surface to reflect the sun's radiation is called albedo, A-L-B-E-D-O. Grass is fairly light in color and reflects 5 to 25%. On the other hand, a dark roof reflects only 10 to 15%, and dark black asphalt absorbs 90 to 95%, reflects only 5 to 10%. That's why asphalt pavement gets so darn hot on very, very hot summer days. Okay, water is an interesting surface because let's say it's noontime, water reflects only 5–10% of the sun's light. A lot of it goes into the water. But if the sun is near, say, sunset or sunrise, the light's coming in at a low angle, and most of it bounces off the water surface, as much as 80%. Okay, so all this scattering and reflectivity influences the amount of radiation that's absorbed by the Earth's surface, that's reflected off the Earth's surface. That in turn affects the amount of heat that accumulates from the sun's radiation at any particular place, and that affects our weather, cloud formation, and in the long run affects our climate. The sun's radiation and the ability of the Earth to absorb or reflect sun's radiation is also what leads to what we know of as the greenhouse effect. The greenhouse effect is influenced by the amount and the proportion of heat-trapping gases in the atmosphere. Among them are water vapor, carbon dioxide, methane, and some other gases. But carbon dioxide is the chief culprit that we are most concerned about now. The reason that carbon dioxide is increasing in our atmosphere is us. We humans emit so much carbon dioxide into the atmosphere through vehicle exhaust, through industrial exhalations, through our own breathing, of course, that it has caused the proportion of carbon dioxide in the atmosphere to rise. In terms of speed of rising, it's been pretty drastic. Since the Industrial Revolution started about 1859, our carbon dioxide in parts per million has risen from 300 or so to now approaching 400. So the way it works is the short wave, the heat from solar radiation, a lot of it's absorbed by the Earth's surface in short wave, and then it comes back off the Earth's surface as longer wave radiation. The long wave radiation is absorbed by CO2 and other greenhouse gases, and then comes back down to the Earth. It gets trapped by, the heat gets trapped in the lower atmosphere. So that's, in a nutshell, what the greenhouse effect is. So we have to worry about this. We have to be concerned about it. We humans are spiking the amounts of greenhouse gases in the lower atmosphere and increasing the tendency of the atmosphere to trap heat. And that's causing all sorts of effects, ranging from sea level rise to more frequent storms, more higher intensity storms, increased prolonged drought, increased fires. It is happening. I don't care what the oil companies are saying. They have a very vested interest in having you buy more and more fossil fuels, and the higher burning, increased use of fossil fuels is what's contributing to this. And by the way, oil companies and other energy companies have known about this effect since the 70s. But what they've been trying to do is make more money by selling more and more of these fuels, which emit more and more carbon dioxide into the atmosphere. So this is something called the Keeling Curve, which is named after a scientist, Mr. Keeling, who was smart enough to set up an observatory in Hawaii near the peak of Mauna Loa, which is a volcano on the island of Hawaii. And he started taking measurements of atmospheric carbon dioxide back in the 50s, all the way through the 90s, and his son has since taken over his work. And he's noted that carbon dioxide concentrations have risen steadily from 315 or so all the way up to 370 parts per million. The up and down that you see here in this curve, the red marks are the actual data. The blue line is the average trend of data. The reason why CO2 concentrations are lower in the summer, as measured by Mr. Keeling, is that plants take up more carbon dioxide during their growing season. That's why there's lower points here. The peaks are in the winter time when there's less tree growth. A broad view, looking at CO2 concentration back in the year 1000 AD, what we can see from tree cores, from looking at carbon dioxide in bubbles trapped in ice, and from other sources, is that CO2 is at 270 or so, 275 parts per million. It's fairly steady, a little bit of a bump here. But then in the year 1850 or so, it started to rise. Why? Well, in 1859, we extracted our first petroleum from an oil well, and we started using it to replace fuels like wood and coal, but that also coincided with the beginning of the Industrial Revolution, where we started to build more factories. Our machines became more efficient. We used machines to manufacture materials instead of manual labor. Those machines, of course, required fuel to keep going, and the fuel was coal, and the fuel was petroleum. We started burning more and more fossil fuel stuff, pumping more carbon and CO2 into the atmosphere, so that the rise has really spiked since then. And of course, there was another spike off of the spike in the 1950s or so. That's when we started driving more and more automobiles. So this effect is real. This effect is happening. We need to do something about it because we're having problems and issues because of greenhouse gas increased emissions, climate change, disastrous fires and so forth, which I've already mentioned. So let's pay attention to that.